Methanol is formed when carbon dioxide and hydrogen react. Table 5 shows some enthalpy of formation and entropy data for these substances. Use the equation and the data in Table 5 to calculate the Gibbs free energy. So remembering that delta G is delta H minus T delta S, but that's for the overall reaction. So the first thing we need to do is calculate each one. So delta H is the standard enthalpies of formation of the products minus the sum of the standard enthalpies of formation of the reactants. So let's add them up. So the products, we've got minus 201 plus minus 242. That's the sum of the products, minus the sum of the reactants. Hydrogen's an element, so it's got a value of 0. So if we add that up, we get minus 49. But look at the units. This one's in kilojoules per mole. Then we're going to do the same thing for delta S. It's the sum of the entropies of the products minus the sum of the entropies of the reactants. So we're going to do the same thing. So the products, 238 and 189, minus the sum of the reactants, 214 and 3 lots of 131. If we type that into our calculator, then what we will get for that, we'll just check. So 238 and 189 minus 214 and minus 3 lots of 131. We get minus 180, but check the units of this one, joules per Kelvin per mole. And notice that this one is in joules and this one is in kilojoules. So we can't combine them without converting one. We've got a temperature here, it's already in Kelvin, so that's okay. So we're going to put delta G equals delta H minus 49 minus T, 890, delta S minus 180, but I'm going to convert it into kilojoules by dividing by 1,000. So minus 49 minus 890 times minus 180 times 10 to the minus 3. And I'm getting an answer of 111.2, but 111 is enough significant figures. And this would be in kilojoules per mole. And it's a positive answer, which means that this reaction isn't actually feasible at this temperature, because the value is positive and not negative. Figure 4 shows how the Gibbs free energy change varies with temperature in a different reaction. Straight line graph has been extrapolated to 0 Kelvin. Use the values of the intercept. So we're saying that the delta G equals delta H minus T delta S is taking the form of a straight line graph. So this part is our mx and this is our plus c. Okay, so our y-intercept at 110, 20, 30, 45. So y-intercept is our c value equals delta H equals 145 kilojoules per mole. Our gradient is going to be equal to minus delta S, because our mx, our x was our t, so minus delta S is our gradient. So let's work out our gradient from our graph. We need to pick some points to create a triangle. I'm actually going to go onto the axes here, because then I can use 0. So that to me is like 850 on the x-axis. We've measured it already, 145 on the y. So my gradient, my dy, 145 over, and it's a negative slope, so if I were to put my differences in, oops, not 890, 850, sorry, we can get a gradient of minus 0.171. This would be in dy, kilojoules per mole, divided by x per Kelvin. So minus delta x equals minus 0.171. So delta x equals 0.171, but remember that is in kilojoules per Kelvin per mole. So if we want it in joules on the bottom line, then we're going to times by 1,000, so 171 joules per Kelvin per mole. So 171 here and 145 here. And in terms of values for your gradient here, anything between 167 and 173 is within the range. State what figure 4 shows about the feasibility. So remember, the reactions are feasible when delta G is less than 0. So this is all these temperatures here that I'm highlighting is when it's feasible. So that is at temperatures over 850 Kelvin is when it's feasible. The answer to that.